underscore incremental anomaly detection dot mlx. So please feel free to dive in, experiment
Now
with
the
the
simulation is
tools,
complete.
and reach out to our TAs if you need any help.
So we
So
fixed
you
one
can
issue that
toggle
now
to
buffer
MATLAB
is at a
online
certain
screen
level, it's
and
not
try on your own. We'll give you
overflowing.
about 4 to 5 minutes.
So far we have looked at uplink scheduler performance matrix. So everything is about uplink, be it blur or be it macler performance. Now can we also look at downlink or both? So let's do that. So let's go back to the model and you can follow along. If you have completed all the 3 tasks, you can follow along. Now look for a variable called direction in your model or the MLX file. Now it says direction is uplink. Now let's change it to downlink and run the simulation. Now again the model is same. But the window now shows downlink scheduler performance matrix. Now these curves are for downlink direction. The simulation is now in progress, so let's complete it and then we can discuss more details. Okay, now the simulation is over. And this visualization is all about downlink, as you can see in the name of the windows, downlink scheduler performance matrix. Now, the left plot is for blur, which is file level metric, and the right plot is for Mac, which is scheduler performance. Now I do see some interesting patterns here. If you pay attention to buffer status, which is the bottom right curve on scheduler performance matrix, you see some peaks here. And we also see peaks in blur in the in the block error rate of this visualization. Now these peaks are appearing at the similar time, as you can see, and we are modeling for 300 milliseconds as we have configured our model. Now these peaks are appearing at the same time. So why is that? So now let's try to correlate the performance of Phi and Mac and let's gain some insights. Now, the default behavior of a 5G network or 5G node is as soon as there is a retransmission or a failure, a decode failure, a transport block results into an error, then the MAC and Phi enters the retransmission. They start retransmitting the same transport block. And that's what you see here. Some error happened and you can see it in the blur. But at the same time, the MAC and Phi start retransmitting. Our application layer is still generating data. Application layer doesn't know about what MAC and Phi is doing down below. Now, as application layer is generating data, you can see the buffer status is peaking at the same time. So you can correlate these two curves and gain some additional insight. And not only that, if you pay attention to the throughput curve, so this is downlink and throughput is from the perspective of the receiver. So here UE is receiving, and you can see as and when the blur happens and there's a peak in buffer status, throughput goes down because retransmissions are not measured to calculate effective throughput. Now, so far, we have seen graphs and patterns and some high-level information about how our network is behaving.
So
But can we
Saurabh
see
is asking how to
numbers?
get TA's help. You can
So let's
type it
go
in the
ahead and
Q&A
explore some
section. They'll be able
statistics.
to answer you.
Now, this is downlink, and we are seeing
And
some
2 more minutes to
errors
go
in transport block decoding.
before we
So
move
let's
on.
go ahead and go back
Hope everybody is able to
to
run
our
it
model.
without any glitches.
And since we have already enabled the statistics, and well, you can see
If not,
statistics
there is
across
a
all the
MATLAB
layers like
Expo,
be it
online MATLAB
app,
Expo
RLC,
community
Mac,
page. You can
Phi.
post your questions there. We can get in
But
touch
here we
after
are
the
printing
session
some
also. So
specific
Please follow along.
statistics value and this numbers in terms of packet counts or transport block counts. Now you can see that decode failure at GNB, that is in uplink direction, is 37, and decode failures in downlink, that
So
means at
moving on.
UE, is 13. Now you can
Hopefully
see
that
some
went
numbers.
well
So
with
after
most
patterns, you
of
can see
you,
some
and you
numbers.
were
Now if we
able
change the
to
channel
find
model to
some
FSKL, where
anomalies
we
in
saw
your
there
data,
was
in the
no
data that
error,
is
these
provided.
failures would be zero.
Next, what we'll do is we'll apply AI for
Now,
bearing fault diagnosis in this task. So bearing fault diagnosis involves
so can we do
multi-class
something more?
classification, and there's something called
And I've
classification
mentioned this
learner app
before
in
that
MATLAB
as we
that is often
visualize the
used for
performance
this
of the
purpose.
network in real
However,
time,
it will
we can also
take a
log the
little bit of time
performance
to train our own
for
AI
post
model. We
processing
will
and
not use the learner
analysis,
app
which
today
we
in
are
the
doing in this
workshop.
simulation.
Instead, we
So
will
let's
train
see
and test model
where
using
the logs are
incremental learning
stored and let's
approach.
explore how you can
We'll
read
work
and
with the
interpret
vibration sensor data we have
that
to
log.
train the model and see if it can accurately
So we are
classify
storing the
different
log
types of
file
bearing faults. Let's walk through the workflow for
here.
this.
The name of the file is
First, what we'll do is we'll
simulation.logs.mat.
split the
So
training
mat is a
data set
standard file
into two
format in
sets.
MATLAB. So
One
let
with
me load
normal
this
and then
these
inner race
logs
fault data, and another one with
here.
for incremental updates that we'll do after
So
training.
once I do that,
Once we split it, we'll
I will be able to
train a
visualize the
naive
logs.
based
And let's see
model
how
with the
it looks
first
like.
set, then incrementally update the model with the second set, and
So logs
observe
are stored in a
how the
variable called
model's
simulation
parameters
logs,
change. Then we'll use
as
the
you can see
model
here.
to diagnose fault types in new testing data. So by this approach, we will see the adaptability and continuous improvement that is possible with incremental learning. So take a few minutes to walk through the task number 3 and we'll again regroup for your review. You can move to MATLAB Online, open T3. You can open the folder, the file that is highlighted, and run it and see. I'll give you 5 minutes to run through and we'll regroup. Two more minutes to go. One of you asked if results can be discussed. We have lot of workflows packed in this 1.5 hour, 90 minutes workshop. So the live script is pretty self-explanatory. And if you're completely new and if you're facing any difficulty of following it, please post it in MATLAB Online Expo community page. We'll definitely get back to you and we can help you ramp up and understand the results. Hope you're done. And all this, the link will be available in GitHub page, so you can take a time for this and redo the workshop after the session ends also. So let's move on. So as many of you said in poll one that you have code generation experience. So MATLAB provides powerful tools for code generation, command line interface, and the MATLAB Coder app. With these tools, you can convert your trained model automatically into efficient C code ready to be deployed on the embedded hardware. Because at the end of the day, the AI application will be sitting in a portable hardware. This workflow streamlines the transition from model development to real world application, ensuring your smart appliances can operate reliably and efficiently. So, this is a task 4 code generation from the naive based model. It is an optional exercise. You can try it on your own later because it takes a little bit time. So, due to crunch of time, have it as an optional task. Now, I will pass it to Elsa, our next speaker, to go through the next section.
Thank you, Tarni. So, hello everyone. Now we have had a look at how to use the machine learning workflow, and we are going to now move on to the second part of our AI modeling, that is using the deep learning workflow for smart appliances. Deep learning is another approach commonly used for smart appliances. Compared to traditional machine learning, deep learning can handle more complex data, it can deliver higher prediction accuracy, it can scale more easily to larger datasets, and adapt more readily to new data. In fault diagnosis applications, network structures such as convolutional neural networks or CNNs offer automatic feature extraction capabilities. This means that you do not need extensive domain knowledge to identify relevant features, as the network can learn them directly from the data. From now on, I'll show you how to build a deep learning model for your smart appliance. Before we move to the hands-on task, let's have a quick poll. You can check your poll tab and answer the poll there. Looks like the poll is posted there. You can answer it now. Okay, I can see quite a few responses coming in now. Right. Great. Thanks, everyone. Moving on to our next slide. Designing, as I was mentioning earlier, we're going to focus on the deep neural network workflow now. Designing and training a deep neural network is not always an easy task. So, to simplify this, in MATLAB, we provide apps for modeling. For deep learning, we ship pre built apps that help automate the training step and provide visualizations for understanding and editing your deep networks. Uh, the first app is the Deep Network Designer app. It will help you access pre trained models. You can visualize an imported model. You can even create your own model from scratch. You can analyze the model. You can export and generate code out of it. There is also another app to manage experiments. This will let you explore hyperparameters, monitor your training progress, define experiments with MATLAB code, and you can keep track of your work and export model results. So now we are going to move to our fifth task, where you will create and train a deep neural network for bearing fault diagnosis. Let me first summarize the steps that we are going to look at in this task. So first off, we'll be loading the dataset as you did previously, and you will prepare data for training valid. Then you'll be defining the network structure, that is the deep neural networks structure. You will be defining your training options, and then you will train the network with GPU. Once you're done with the training, you will then evaluate the model with new testing data. And finally, if you want, you can save the model for future use. Okay, so as you can see on your screens now, you can navigate to the script which says T5 Deep Learning Fault Diagnosis. And we will spend about 5 minutes to run through each section of the script as you did in the previous task, and then we will regroup and we can discuss any questions that you might have in the chat window. So I hope all of you are able to navigate through the sections. I can see a few thumbs ups, but let us know. We have about 1 minute left for you to try it out. Okay, great. I see a lot more responses now. Thank you. Okay, so hope we have finished running through the script. So now let's move on. So we tried out creating and training the deep neural networks. Once you have a model trained, you can use our unique code generation framework that allows models which have been developed in MATLAB or Simulink to be deployed anywhere without having to rewrite the original model. This automatic code generation eliminates coding errors, and it's an enormous value driver for any organization adopting it. Deep learning, deep learning models are often resource intensive, which means that they require substantial memory and computational power. This presents a challenge when you deploy models to edge devices where onboard RAM and processing capabilities are typically limited. Embedded systems, in particular, must operate within strict hardware constraints while still delivering reliable performance. To address these challenges, it is important to leverage network compression techniques. Methods such as pruning, projection, and quantization can significantly reduce the size and complexity of your deep learning models. By applying these techniques, you can optimize the models for edge devices without sacrificing on your accuracy too much. Now, there are three types of model compression techniques offered by MATLAB. We recommend you to implement them in the order of pruning, projection, and quantization to achieve the smallest model footprint while maintaining accuracy. This does not mean that you have to implement them all. Pruning is very powerful for convolution layers, and it refers to removal of learnable parameters that have the smallest impact on the prediction of your network. Projection is a way of converting large layers into one or more smaller layers with fewer learnable parameters. And lastly, quantization is a data type compression technique. So here you will reduce the precision of the parameters in your network, but the amount of the parameters and the network architecture will still stay the same. So the network pruning tool provided by MATLAB uses first order Taylor series approximation to remove redundant convolution filters from your convolutional neural network or your CNN. You can apply this technique to both one-dimensional and two-dimensional convolution layers. Uh, you will need to retrain or fine-tune the network after pruning to recover the accuracy. The projection tool provided by MATLAB reduces the number of learnable parameters of your layers by performing principal component analysis or PCA of the neuron activations using a dataset which is representative of the training data. It then projects the learnable parameters into the substate that maintains the highest variance in neuron activations. You will again need to fine tune the network after projection to recover the accuracy. Once the model has been compressed to an acceptable size, we can generate code for edge deployment. You can use different coder products to generate code for this model for different targets. Here we'll be showing the workflow of generating C code from Simulink. Implementing deep learning networks in Simulink with layer blocks has a lot of advantages, like visualization of the network. Using Simulink blocks is very intuitive. You can debug intermediate values of network activations. You can even trace specific layers to their implementation in the generated code. Uh, so now we will practice compression of the model using network pruning, projection, and quantization. When implementing these, careful choosing the hyperparameters which achieves the best balance between compression and accuracy. So some of the parameters for pruning are the maximum number of filters to be pruned, the maximum number of pruning iterations, etc. For projection, the target proportion of neuron activation variance explained by the remaining principal components. And for quantization, you should choose the proper data type so that it balances between numerical precision and model size. So now let's dive into the task, where we are going to actually compress the deep learning model that you created for deployment. Just like before, I'll summarize the steps in the task first, and then you can open up the script. So the first step is to load and analyze the network. The second step would be to compress the network by pruning. We'll follow this up with the next compression process, which is projection. And finally, we'll compress the network using quantization to int8. So again, the script that you need to open up now is T6 underscore network compression, which has all of the steps that I just summarized now built into a test section. So I request you to run through it section by section. We'll spend about 7 minutes here to run through and then regroup. As always, do give us a thumbs up when you're done. I think this script might take a little more time to execute. Yeah, getting a few responses now. Thank you. So while you're finishing up, let's have our fourth poll. I request the TAs to publish that, and the attendees, if you could just respond to the poll appearing in your polls window. Okay, thank you everyone.